Good morning.
Good morning. Someone commented that they can't hear. Can you hear me? Anything, thumbs up? Okay, so I guess we will go ahead and get started. I will share my screen. Okay, can everyone see? A couple of thumbs ups, or you can use the reaction, the reaction button. My name is Elena Newell. I am an assistant professor at Baylor College of Medicine in the Center for Educational Outreach. A lot of what we do in the center is related to teacher professional development and curriculum development in health sciences and all sciences, really. We also are home to faculty liaisons for two health magnet middle schools, BCMA at Ryan and BCM Biotech Academy at Rusk, as well as the DeBakey School for Health Professions. So we've got a couple of different connections to schools in HISD specifically, and but specifically I work pretty closely with our two middle school liaisons. I myself am a measurement quantitative methods person, so if you have questions about qualitative, I might not be as much help with that, but I certainly will help get started. So today the real focus is a true introduction to data analysis. So if you are highly familiar with data analysis and you already have students who are doing advanced statistics, like they're doing ANOVAs or advanced regressions, this is probably a little low level for you and you're gonna be bored. So I'm gonna let you know off the bat. If you are like, I don't know where to get started with my students, I don't know how to help them organize their data, I don't know that we're doing the right things, you're in the right place. So this is definitely a true introduction. I could teach an entire course on statistics, so this is just dipping a big toe into it, and it's a little bit more targeted towards the lower end of the spectrum. So some of the high school students probably know some of this information. Middle school students might be still adjusting to it. So just to let you all know the level that we're at today. So this is what today's agenda looks like. We're gonna be getting on the road. So thinking about the road to results, if data analysis, if our goal is to get results, then how do we get started? Because what you do before you do your analysis is more important in a lot of ways than what you do during your analysis. If you set yourself up for failure from the beginning, there is no saving it through any statistical technique. It's already dead on arrival. So what you wanna do is get on the road in the right way. And then a quick overview of steps in data analysis, specifically quantitative data analysis. And while this can vary depending on the approach that you choose to take, and especially if you have students who are already pretty strong, these are kind of your basic intro steps. I won't be going deep into statistical techniques like looking at your more advanced stats, but I'll touch just a little bit on inferential statistics, which is where we get into our t-test correlations, things like that. And then a couple of resources that I find particularly useful to help you get there. So, okay, so So if we look at this, and people have a lot of, when they look at research design and process, people have a lot of different ideas about how it should go. This is a pretty general one, right? It's, you get a topic, you do some literature review, you develop a question or a hypothesis or both, you develop your study and your procedures, you collect your data, then you analyze your data, you interpret it, and you report. Easy peasy. And data analysis, typically, a lot of people, even in our faculty, won't start thinking about how they're going to start analyzing their data until they get to that point. They're like, I've got all this data together, great. I'm going to stir it up in a pot, and I'm going to come out with some kind of analysis that I am then going to interpret and write things up. It's going to be lovely. But what you have to think about is that data analysis is something to really focus on all the way through this road. You want to think about it during the planning process, because if you don't, again, you get back to a situation where you don't have the appropriate data for what you want to do. So it's really something to think about during each of these steps, as you're formulating your question, as you're developing your study design, and as you're collecting your data. Your analysis should be a part of that process. So I want everyone to take a moment, think about a science fair project. It can be one that you have used in the past. It could be one that you are interested in. It could be one that just came to you off the top of your head. And then drop it in the chat. Let's get an idea of what kinds of questions people are looking at. It can be complicated, it could be simple. And even if you don't want to drop it in the chat, definitely write it down, because I think going through this process and thinking about questions that you've seen in the past, maybe it was one that a student struggled with where you couldn't figure out how to analyze it. Maybe it was something that you would just like to see have done better. If you can write it down and think about it as you're going through the presentation, then in the end, you can ask targeted questions about that and maybe come up with different ways. Okay, testing different brands of glove for leak resistance. All right. Any others? Energy recapture from air conditioning exhaust. All right. How can we reduce microplastics in the ocean? The role of local plants to support birds migrating early. Okay, so there's some really great questions here. And some are really complicated. And I mean, I think these are things that are being actively researched by scientists at all levels. So these are great questions. Okay, so the next thing I'll say, and how many of you were in the question session just before this that were thinking about generating questions? You get hands, waves, reaction. So one thing that I like to do when I walk people through this process, and I do this with our faculty members too, we have faculty members that are engaged in educational research, is I ask them to look at their questions and identify what their variables are. Especially in younger students, sometimes they don't think about their variables. And if you haven't thought about your variables, then how do you know what to measure? So take a moment and maybe write down next to your question what your variables are. And keep that in mind as we're moving forward. So this is the question that I came up with, and it's going to be our example that we're going to run with through this entire presentation, just as a nice, easy, kind of straightforward approach to data analysis. And it's one I've actually seen before at the middle school level in a school science fair. So which color makes plants grow the fastest? And what's the first thing that you think about this question? Any comments? Like, how are you going to analyze this? Okay, photosynthesis, yes. But okay, so more specifically, how are you going to analyze this? What's your, if you have to say, okay, I've got a question, I'm gonna, okay, light type, yes. Plant height, which plant to use, time, collection of heights over time, yes, all of these things, brightness, color, height, yes. Okay, so you all are exactly on the right track. And a lot of what I typically do is say, okay, let's move forward. Okay, yes, let's identify immediately what we're doing. So comparison, what our variables are, what we're going to be measuring and when. And then let's make it more specific. Especially with younger students, it's a lot easier to say, okay, let's drill down more, be more specific. What are we looking at? Because initially, if we just say what color light, well, okay, if we've got 3 light colors, let's be specific. It tells you immediately, okay, what are we measuring, what's going on, and this helps with the analysis process as well as the data collection process because you know what you'll be doing. So the next thing I ask is, how will I know when I have the answer to my question? So I don't know if many of you, I'm sure a lot of you are familiar with the backwards design approach to curriculum development. If you've used it before, you know that it's always starting with the end in mind. And it's not all that different with data analysis. You're starting with the end in mind. You want to think, okay, what information do I need to be able to answer the question that I've come up with? I got really specific. I know what my variables are. How will I know when I have the answer to this question? Because the point of analysis should be to provide you with information to answer your question. So from the question you wrote down earlier, take a moment and write down a sentence. If you were going to have a concluding sentence or a summary sentence of what your findings might look like, what should they look like? And I encourage people to do this with students as well, because not to say, in a lot of cases with hypotheses, they maybe already are thinking in that way, but if they have a question on its own, what information would they need? It gets them thinking about what it should look like. So not to predetermine what their findings might look like, but to predetermine what they need to measure to get to those findings. So with my example, okay, thinking about what the answer to this research question might look like, there's a couple different approaches you can take. So this might be something that if you asked a student right off the bat, what findings look like, they might say something like, okay, plants in the red light grew the fastest. And then I'd say, well, how do you know? What's your evidence? What's our next step? What do we need to see? So this might be a sentence that I might expect to see. So plants in the red light grew the fastest, they increased in height, an average of 1.5 centimeters each day, and they went from there. So at this point, you know that what you're measuring is you need height over days and some number of days. So you already know you have to have multiple measurements. And this is an issue that needs to be clarified because this could also be the answer. If you said, okay, this is the height at the end of 6 weeks, and you only have one measurement. So I think really getting at this kind of concluding sentence and deciding what the data collection can look like or what you need to be able to answer this question and what's going to be sufficient is a really good exercise, especially for students who might not have thought through clearly what they need to collect. Okay, so again, this is just reiterating that difference that we have between the data collection process during the planning for when you get to your analysis. You've got the 1.5 centimeters per day, so you know you have multiple days of measurement, and then 19 centimeters at the end of 6 weeks, so you have one measurement. So helping students think in terms of how this final sentence or final summary, what that will end up looking like when you do your analysis. So, okay, trucking along, got the question, you've got your data collection plan, what's next? So generally, I like to say that a tool is what you make of it, and statistical analyses of any types are tools, and you won't know how to use them correctly unless you know what you're using them for. So we've got our question and the materials that you have and the nature of your data. And I know all of you are familiar with nature of data, but I'm going to go through them right now just as a reminder, but also to point out some areas where I see pitfalls in analysis. So scale of measurement is a big thing, and you want to make sure that you're measuring in the right way for the analyses that you want to do. So as a refresher, they're the values of the measurement. They help you determine how to interpret your data. If you have a nominal scale, which, as you know, is when you have a name or identifier. So in my experiment, it might be plant number 1 through plant number 6. Let's say I have 6 plants. Those numbers don't mean anything in as much as they are just names. JJ Watt is not his value of his number, it's just an assigned number. He could be the purple pony and it wouldn't change at all what that number meant. So keep in mind with students who are trying to play with different values sometimes, that they need to think about the scale of measurement, especially for nominal. Ordinal is another one where I see a lot of issues. even with our faculty members, I see these issues because we assign a value for them in terms of a rank order. And you see this a lot on surveys, right? It's like from a scale of 1 to 10, how much did you like this? How much did you like that? And then people will use that and do a mean or another kind of analysis on this data. And you can, in some ways that can be acceptable, but you have to be really clear on what you're doing and why. The problem is that if I'm looking at a scale of 1 to 10 of happiness, how do you know that that's the same as your scale? And how do you know what the difference between a 6 and a 7 is? So what people end up doing is using statistical analyses that are meant for data with even spaces or with a true zero or other attributes that aren't necessarily valid for ordinal data. So they really need to keep in mind, is there a true difference between these values? What is the interpretable difference between these things? When you go to do an analysis on ordinal data, maybe it makes more sense to summarize the number of people who selected each number as opposed to doing a mean or in addition to the mean. So thinking about what the data actually is and what it means is really, really important. And when given an option, instead of maybe saying, okay, well, I'm gonna have people pick different values. How much do you like, or you know, how often do you do this thing? 1 to 5 times, 5 to 10 times, 10 to 12 times. If you have different levels, does it make more sense to ask for a whole number if you want to do advanced statistics with it? By reducing that and reducing this ability to get at some of these, to use different analyses, you can handicap yourself in some ways. So ordinal data, really do keep in mind the value of the different numbers that you have. So again, interval data, keeping in mind that there's no true zero. And this, I see issues more in terms of the interpretation phase, when students start writing up the differences between things. You know, as I use in the example, the distance between 60 and 70 degrees and the distance between 30 and 40 degrees is all the same. It's 10 degrees, but you can't use that value in the same comparison because there's not a true zero. So keeping in mind, like, what kind of data am I collecting? What do these numbers mean? Where am I starting? Ratio data is typically where we end up with a lot of quantitative things, and it's what you need for the most part when you're doing statistical analyses, especially those that go more advanced. So if you're thinking about having your student pursue a regression analysis, categorical data, so our nominal data can be used for a category. For instance, our light color in my example, those are categories. We could name them lights 1, 2, and 3, but they're categories. The ratio data is usually where you want to end up, and you can do it with interval data as well, but ratio data is typically where you want to end up for most statistical analyses because there's a true zero, there's meaningful distance between each of the values, and it makes sense to say things like this is twice that, and you can put things in context. So this is why, even though scales of measurement seems like a fairly fundamental thing to look at, it's really useful to sometimes double check and ask yourself, okay, what do these numbers mean? What am I measuring? And why am I measuring it in this way? Is there a way I can get more exact or more precise with the numbers that I'm using? So again, just to recap, it determines how you analyze your data, and you have to know the kind of data you're going to collect as you tackle your research question. Sample size. So sample size is a pretty big issue, especially if you get into more advanced statistics. So if you have a student that maybe has a mentor and they're going to do something more advanced, usually the mentor will help them with this point, but it's something to think about regardless. And I would love to hear comments from people. Why do you think sample size is important? And you can put it in the chat or you can shout it out if you so feel inclined. Variability, outliers, relevance, yes, validity, minimizes bias, increases reliability, material sample size, yes, can render how statistically valid the data is, yes, enough randomization. Okay, so these are all really great answers, and I will make 2 points, and again, these might be things that those of you at a more advanced level are really familiar with already, but I want to cover just in case. Sample size is not just the number of subjects, but it's also the number of repetitions per subject, and there's calculations that go into figuring out what your exact sample size can be, but also these are the main, sort of the main things that we think about when we think of sample size. So of course the practical, you got limited time and resources. You can only do so much. I'm a quantitative person. I'd love to measure everything. You can't. Ethically, you shouldn't, especially if you're using living things, whether it's a slime mold or a person. We should only use what we absolutely need to in order to get to our results. And then analysis. And you know, the main reason how I would boil it down in terms of analysis is that some forms of analysis will not work with small sample size. And in fact, the more complicated you get, the bigger the sample size you need, mostly because inferential statistics are trying to make inferences from a sample to an overall population. And many of the things that you mentioned in the chat are dead on. If you have a small sample and there's an outlier in that sample, then your inference is totally thrown off. You've got an inference made off of a non-representative sample. And it's harder to tell that when you have a sample that's too small. You don't know. You think that that's representative and it's not. And so most of these analyses, some will run. So if you have a student, they figure out how to run analyses and they're not really familiar with it, some of the analyses will run, they'll work, but the inferences will be faulty. And that's the problem that you'll run into. So it's really important that students keep that in mind when they're going to do something. If they don't have a mentor, a lot of students won't maybe end up using inferential statistics, especially the younger ones. But if they do, there's several online calculators that can help. If they're going to do something incredibly fancy, then I suggest that they work with a statistician to figure it out, because it's one of those things where if you've got multiple groups and they're nested inside of other groups and you've got different variables that are associated, then it has to be very carefully planned to make sure that the inferences are correct, because that's the whole underlying reason behind sample size and sampling in inferential statistics, is making sure that your inferences are correct. So this is one example of a sample size calculator. It's pretty straightforward to use, and it's pretty, I like it for simple research designs. If you have something more complicated, again, you probably want your students to work with a mentor or someone who is pretty skilled in stats to get them on the right track. There's also a software program called G-Power that is used, and it for more sophisticated stats as well, that students can play around with. It's like a computer add-on, and it's really, really useful. You have to do some background research into what the different aspects mean. But again, it's something that it provides another option if students want to explore. So we're going to jump now into steps in quantitative data analysis. Before I get there, does anyone have any questions? So we can, before we transition, I will take any questions on any of the pieces that I just did before we jump into the next. Okay, so we'll keep going, but do feel free to jump in with any questions that you might have. I'd be more than happy to answer them. So we're going to look at quantitative data, because qualitative data, and those of you who were in the last session noted that there was a conversation on qualitative data. Qualitative data on its own, of course, can be analyzed, and there are very specific steps that go along with that process as well, and not even quantifying the data, but genuinely using the qualitative data, they're written, like if they have essays or they're looking at tweets, there are ways to do analyses on them. And in fact, there are some really cool, for those of you who have high school students that are looking at more advanced ways of going about doing a science fair project, Cinnamon analysis is super cool. It takes some coding expertise, and it takes students really putting in a lot of work to figure out some of the approaches to it. But looking at, you know, tweets on a certain subject or other publicly available data can be really, really cool, because the way that we use language, of course, is its own kind of data. We're not doing that today. Today we're looking at quantitative, and we're going pretty basic with it. These are just the steps that I usually recommend for anyone getting started. I use this in my own data analysis, and it's a good way to start for everyone, regardless of where they're going next with their data for the quantitative side. So back to my example, just as a refresher, what it looks like. So we've got 3 light colors, we're looking at height, we're looking at time. So I love spreadsheets. I use Excel for everything. I even if I'm planning a vacation, I will put it in Excel. I just think it makes things much easier to read. And so this is from our example. I've made some fake data to put things together. You can do the same thing in Google Sheets or any other spreadsheet program. And generally the way I lay out my data is like this. So I usually do subjects with rows, with their own individual rows, and I make sure that the independent variable is in there as a label as well, so that I can differentiate. From there, I usually do dependent variable in the columns. If it's by time, then it's each measurement point has a column. If it's by different characteristics, then they each have a column. And I try to make sure I have the measurement in there and leave nothing but numbers in the cells, because it's a lot easier to do things directly with this data in the spreadsheet with the cells. So yes, units of measurement in the column name. I recommend keeping your students consistent with their formats. So it sounds like not a big deal. What does it matter if it's 0.0 or just 0? I think in being precise with your measures, if you're going to have everything be 1 decimal point, keep it consistent throughout. The other nice thing about keeping your data this way is that you can check for errors as you go. So you can see, you know, from one time point to the next, it doesn't make sense that we've got a decrease and then an increase again. Should that be 4.8? Possibly. We've got day 32. Why is that day 32? Did we go backwards? Is that in the wrong order? So I think keeping track of data in this way and giving it a good clean read over is something that everyone should do. And in fact, usually I take it a step further and I keep my independent variables as their own column. This allows you to sort. If there are multiple independent variables, especially, you can sort by them. If I had color as well as a room temperature condition, I could look at just the room temperature and I could look at just the color, and it allows for an opportunity to get a general idea when you go to summarize the data. So I highly recommend spreadsheets, and I highly recommend a very systematic approach to putting your data in the spreadsheet, whatever it is. If it makes more sense having the subjects having each measurement be on a line, and so instead of being subject plant 1 through 6 with multiple days across, maybe there's 3 columns. It's subject, light, color, day, and a measurement, and then a measurement column. And then you can sort by all plant 1 or all plant 2. It really depends on the best way for grouping your data, because the next step for most analyses is the descriptive statistics. Everyone should do this. I don't care whether you're doing a super advanced analysis after the fact or not. Summarizing and describing your data is the best way to identify any cool issues in the data, any major issues from data input also. But if there are cool things that happen and you're like, well, this is weird, why did the green group do this? You can see that immediately. And so usually if I have multiple independent variables, I will go by both. So I will aggregate by individual groups, so red and cold, if I had the 2 independent variables, or I would do all the cold and all the red, and I would look at them in aggregate to get an idea of what the analysis will look like going forward. It also gives you a perspective on the nature of your data, and specifically for advanced statistics, the distribution. I want to know if there's normally distributed data or not, and I'll touch on that a little bit more in a second. But going back to summarizing, central tendency is usually where students will start. Means are probably what most students will end up using if they have ratio count data, things like that. But don't let them forget that there are other potentially better ways of summarizing their data. And a lot of ordinal data, it can make more sense to have a median. Maybe the mean doesn't mean anything. In some cases, the mode, if you've got a bimodal distribution on your ordinal data, if people said, if you have a 1 to 5 scale on how much did you like a session, and you've got a lot of 4s and you've got a lot of 2s, sometimes it makes more sense, instead of having a mean that ends up at a 3, it makes more sense to say, well, we had a lot more people at the 4 and we had a lot of people at the 2, so there's something going on there. It can be really useful. So the use for which types of data at the bottom is a bit simplified, because you can use these for lots of different approaches, but this is one way to look at things. It's a way for students to get started. And then again, this is a quick reminder, one, about the measures of central tendency, where they end up, but also keeping in mind that any student that is going to do advanced statistics needs to know what the distribution of their data looks like. So ideally, it would be a normal curve, and some more advanced statistics will be forgiving with this, but if you have a lot of skew or kurtosis, which is where that hump is really, really skinny or really, really wide, if that's an issue, then again, some of your analyses might not work because they all come with underlying assumptions that will impact the inferences that you can make. So group 2 is, as I mentioned, the aggregation. I usually go by group. I include the sample size information because that would be the first thing that anyone's going to want to know, especially if the groups are different sizes. So if I've got 7 in the red group and I've got 3 in the green group, I need to know that. It needs to be somewhere. And then just looking across the aggregates, these are means. And of course, I label it as such so that I know. And so taking this data and putting it into aggregate gives me a better idea what's going on. I usually do standard deviations as well with my ratio data, but it can depend on what your data is. In some cases, it might make more sense for the range, but you do want an idea of what your distribution is as well, especially if you're dealing with a lot of data. Or in this case, I mean, there's very small amount of data, and if you look at blue light plant number 1, it never grew. So when I'm looking at the means for the blue light plants, you know, is this representative of what my data actually is? Maybe, maybe not, but it's helpful to have some measure of distribution as well. So when you come up with a final table for this, standard deviations are important to include. I didn't in this particular version because I used this then for figures. So jumping into visualizations, which again is my third step regardless of what I'm going to do with the data next, because it's easier to catch errors or interesting things in the data like a bimodal distribution if you can visualize your data first. It's helpful to readers, it's helpful to you. It's an interesting way to look at change. So I've noticed that I see a lot of people using the wrong kinds of visualizations. There's a ton out there, but sometimes it's not as helpful as it could be. So again, my example, just to bring y'all kind of back to the beginning. So in this case, line graph makes sense, right? We're looking at things over time. So you want to show progression. It also implies that data points are connected. And I've seen people use lines before for things that aren't connected. And I always wonder why, because there's something that's supposed to be happening in that line space, that there's an implied connection from one point to the next. I also would note that spacing matters. So in this case, one, if I did this authentically, I would have started with day 0, not day 1, just because I feel like having 0 on my x-axis makes more sense, because it truly is the start day. But here, we've got spacing and it's got day 5 and day 7, because sometimes measurements don't happen right on time when you need them to. Makes sense. We can still do our calculations about rate and change and everything like that without doing so. The problem is this is misrepresenting the data. So this is what it should look like, right? Where we have a measurement on day 7 and a measurement on day 5, and they're closer together. And it makes the data look the way that it should. So you have a better idea of what the curve looks like. I will note that if you do use Excel for this, the way to make the updated chart versus the original is a line graph. The updated is a scatter plot with lines. So sometimes familiarizing yourself with a different chart, especially in Excel, can help a lot. But it's something to note when you're looking at the data and how you're representing the data as you move forward. So histograms, again, they look a lot like bar charts, just their purpose is a bit different. And actually it's the area typically under the bar that is influential or is what matters. It's not necessarily the height. Usually they correlate. But if you're using a histogram versus a bar chart, when you use the language, it's helpful to be a little bit more exact with it, just in terms of understanding. But it's used to group data into bins. So we've got petal length here in centimeters, which means that everything between 4 and 4.5 is grouped together, and it's basically making your continuous data, your ratio data into ordinal data in some ways, which can be helpful to look at, to visualize, but might not necessarily be helpful in terms of your analysis. It's something to keep in mind though. And then I got our bar chart. So this is where I took the data from the fake plant study and I put it in a bar chart, because you can also look at things over time with this. You can use bar charts for a ton of different things. I probably use at least one in every report I've ever written, because they're so easy to like instantly identify differences and comparisons. It's just really important to think about how you want to compare things and what and this is where it goes back to the question, identifying your variables and what the important things to note are. Usually I use independent variables to be the bars. In this case, I picked one if I had both color and temperature. Then I'd have, sorry, what I meant was I would pick one if I had both color and temperature, or you can change the pattern related to them, or the grouping. I could do cold and then go by color, but it's important to think about your organization based on your questions and based on the organization in your table, which is why starting with organized data initially will help you with your visualizations later. And again, beginning with 0 at the x-axis is really helpful. We started a lot of different places with these. And sometimes they misrepresent data. So wherever you start with things, it's important to note that if your x-axis is somewhere different, it's important to note that. So I like the horizontal version if there's a lot of different categories. One, it puts all of your text horizontally so you can read it, versus if it's at an angle or if it's up and down on a vertical, it can be really difficult to read. And then it lets you give an instant comparison visually across, which can be really useful as well. Scatter charts, usually for associations between variables, really, really hard to do if you don't have a lot of data points. I usually recommend a line. If your students know how to use a regression line, that can be useful. If they don't, I would recommend a different approach to data visualization, because without this, it's really difficult to understand. Even in more dense data points, you can end up at a point where it's just a blob. And then what does it mean? And it might be interesting to know that it's a blob. And in some cases, you can see the blob is kind of U-shaped. So you've got a kind of a curvilinear relationship, or maybe it's like there's exponential growth, and you can start kind of sorting that out. But generally, your end result, you probably want to be able to identify the pattern a little bit more cleanly. So here's an example where the authors actually put 2 lines in. They put a regression line in as a trend, and then they used a non-parametric technique where instead of going a straight line, they tried to actually fit it to the data. And these can be useful, especially if you go into a bit more detail in your interpretation about what these trends mean. And then pie charts. People love pie charts. They're great. They're great for seeing especially pieces of the whole and the relative amounts in comparison. But the number of categories, like this is really, really difficult. If I look at this, I'm like, I don't know, okay, where's Brazil, which percentage, I don't know what's going on. So if you have students who are like, I'm gonna use a pie chart, and they've got, I would say, more than 6 or 7 categories, and especially if some are very small, a bar chart makes much more sense to do for your visualization. This just doesn't mean anything. It's a really pretty color wheel, but it's not gonna, you should be able to look at any figure and have an idea. You should be able to see clearly what the data is going to say. Your description of the data should be secondary in a lot of cases to what your visualization looks like for your final results. So these are general rule of thumbs. There's a lot out there. There's, in fact, several people who do a lot of work on visualizations and the way they should work and the best ways to go about them. But consistency is key. Your colors, your textures. So if you have like a pattern within a color because you want it to be in black and white, it should all be consistent. Your numbers should be consistent. Precision is really important with that. Readers should be able to view what's on there. If your titles are too long for each category, it makes sense to use an acronym or some other kind of label and specify later. If it's not readable and you can't glance at it and have an idea of what's going on, then it's really complicated. It's like you should be able to glance at a roadmap to go somewhere and have an idea, okay, we're going north. If you find yourself zooming in or like moving the map over, then probably you're not on the right map. And that's what this is. You should be able to look at a figure and have an idea what's going on without having to spend 30 minutes trying to discern something or wanting to zoom in or move things over. It should give you direct access to the data and what's going on. Also, misrepresentation in data is huge. you might have seen it before, and occasionally there's great examples in statistical literature where, you know, people have a bar chart and it looks like there's a huge difference. But if you have it on an accurate scale, the difference is quite small. And so while you do want to highlight differences and you want to highlight interesting features in the data, you can't misrepresent it. Okay, this is a chart that I love, that I still use sometimes, and it shows just how expansive data visualization can be. There are so many different ways to look at data and so many different ways to go through for every kind of relationship. There's infinite possibilities. And so if you have a student that's particularly interested in expanding upon their visualization, they don't want to keep it simple, there are so many different ways out there. So I highly recommend letting them know that they can expand and find different ways to present their data. And especially if they, in their literature review, find other people who are doing something and it's a really cool way to present the data, have them look into it, have them explore the different kinds of charts and graphs and visualize in the best way possible. So I'm now going to touch on inferential statistics. Even if they're not used by everyone, I think the ones that I'm going to show are fairly straightforward, and a lot of you are probably familiar with them. Again, it's inference from the sample to the population. A lot of these can be done in Excel or in fairly straightforward, freely available software. Most start, again, with the assumption that your data is normally distributed. So that's something to keep in mind. So t-test, I'm sure many of you have heard of t-test. I think that even middle school students can easily do these. I guess it's the most important part, though, is that they have to understand what they're doing and what the test is actually looking at. But these are specifically for two groups and for means of two groups. So again, going back to your data, you have to have ratio data. You need to have, or continuous data. You can't do this with ordinal data without some transformations or without it potentially not being valid. It's generally looking at the statistical significance of the difference between the groups. And you can do paired t-tests where you're looking within groups, so pre to post test t-test, but I think these are straightforward enough that a lot of students can do these without straining too much if they're interested in taking the next step. And then, of course, correlations, which were mentioned a bit in the previous session on questions, you know, correlation not equaling causation is something really important to hammer home regardless. And I'm glad I had taken that particular comic that she shared out, but it is very true. It's something to hammer home. It's something that we sometimes forget when we read news articles and look at things, that correlation does not mean causation. But correlations can be really important to look at. That's the important first step in a lot of research is there a correlation there? And if so, what direction is it in? And if so, is it something that we might be able to use going forward? So I'm going to run through some resources because we're getting close to the end of time, and I want to leave time for questions and also leave time for people to discuss their specific questions that I had you all come up with in the beginning, if you'd like to, and ways to tackle that data analysis. So the National Center for Education Statistics is an amazing site. They have, their main site has access to large data sets also, which is really cool. But they have all of these kid zone pieces, and the create a graph section actually has a tutorial that you can go to, and you can see it here in this box that will walk students through how to create it, why they're doing it, where their approach is. There's a lot of different shapes and options that go with this. I tend to go with the simpler the better. If there are too many, if you make a graph and you have 3D aspects to it and things are moved around, do I have to spend more, is there more cognitive load on me because I have to figure out where the bars actually are versus looking at the data? You want to be able to look at it, identify it, say, ah, there's a trend, and move on. So while it's tempting for students to make all kinds of stacked and 3D and interesting shapes, that's probably not the best way to represent the data. So I recommend this. It gives a lot of different options, and it helps walk students through ways to create these different graphs, and they can actually print them from there. So they don't have to have Excel if they don't necessarily need to. This is probably better for advanced students. So if you've got older students who want to do a lot of different kinds of charts, some of the ones that I talked about in the big chart chooser section, this is a good place to go. And the cool thing that they do is they have where you can go through the chooser. So these are all the different chart types for 2 points in time. So I'm looking at you can look at slope, you can look at clustered bar, you can look at stacked columns, different kinds of approaches to it, and they still have to have an understanding of what their data is and what they want to display. But especially for older students who might want to do something a little bit more complex, they have an opportunity to look for different ways to choose that, and they can look at their data in different ways. So maybe they start with a clustered bar and they realize this isn't telling me anything. I don't understand what this is supposed to say, because ideally you can take a glance at their whatever chart or visualization they've come up with and say, oh, you've got a trend. And if you look at it and you're like, what is this telling me? Then they need to go back to the drawing board and pick a different visualization for their data. The American Statistical Association, I recommend this for teachers more so than students, but it has a ton of resources for different lesson plans, for different approaches. If you find a bunch of students in your class are really interested in taking the next step and doing t-tests, or they want to know more about what is a p-value, why do we care, and where do we go wrong with p-values, because there's a lot of that. Just because something is statistically significant does not mean that there's a practical significance to it. There's all kinds of things that go into that, and it can cause real problems, especially if you're interpreting things incorrectly. So if you are looking for resources, there's a lot on this page, and I love this organization. Again, quantitative person, so this is right up my alley, but this can be really, really helpful for teachers specifically. And then, of course, this was mentioned before, but there is a crash course video. If you're like, I just need the basics, I need to know now, I need to know in depth, I need to know about probability and uncertainty and confidence intervals, and you want to jump into that, this video is not too terribly long. It's only about 45 minutes, so you can watch it while you eat lunch on a weekend day or something like that, and they go through the basics. So it is a good resource that's out there. Okay. So we've got some time left. I have my email at the bottom there, so always feel free to email me if you want to know anything more about statistics in depth, if you want more resources, if you also are interested in just knowing what we do at the center. If you have any questions about that, you can reach out to me. But in the interim, any questions? Let me go back to the chat so I can see. Oh, you're all very welcome. Be available to post for our science fair students. It's a great resource. Yes, yes, I can make it available. Let's see. Yes, so yes, I can make the presentation available to everyone so that you can use this. There are so many different ways to go about tackling data analysis, and I know it feels very daunting to students sometimes to get started. Like, how do I do this? I don't know what these numbers mean. Math is hard. And believe it or not, I hated statistics. The first statistics class I took, it wasn't until I was an undergrad, and I was like, this is crazy. It was all probability with pulling marbles from a hat, and I was like, I don't know why I need this. And so seeing this in action, seeing how we can use data to make decisions or to understand things better is really, really helpful. Well, thank you guys. If anyone has any questions, I will, the gift of time is always very useful. So I am more than happy to stick around for a little bit and answer questions where needed. And if not, I will bid you all a very happy Saturday. I hope you enjoy your weekend, and thank you for being with me today. To get that visual for different kinds of, so Jodel, before your comment disappears on the long list of things, would you mind specifying what you mean the visual for get that visual for the different types of graphs? You mean the slide with the chart? Is that the one that you're referring to? If so, it is in my, the email is or the website is on the actual slide, but when I share the slides also, you'll have access to it as well. Yes. Stats go quickly, Anthony. I'm right there with you. Even things that I don't use on a daily basis, I'm like, oh my goodness, I've forgotten how to do this thing and I have to go back to it. And actually, so my bookcase behind me is my stats references bookcase, because sometimes people ask me things and I'm like, I have not done that since grad school, so I have to revisit it. It is very helpful to sometimes revisit, especially the assumptions for some of those inferential statistics, and understand why they may or may not work sometimes. To use the uncertainty of the instrument as a basis for determining the number of decimals or significant figure. So there are a lot of things that go into the number of decimals or significant figure. Uncertainty in the measure is a big one, but it also depends on what you're using the data for. The infuriating thing about most of us who do stats is our answers are 99% of the time, it depends. I would say, as a rule of thumb, yes. However, it can get really unwieldy also if you have like 17 decimals, and practically you might not need that many. So it really depends what the data is and what you're using it for. I know that's probably not exactly the answer you're looking for, but I don't want to say, yes, do that, and then it ends up being far too simplified. Thank you, guys.
Any other question, guys? Don't be shy.
Screen sharing so I can see everyone. Yes, I can do that. I can share it in the chat. Let me.
I have a question while you work on that, Dr. Newell. Where can we find information if we wanted to do qualitative analysis? Do you have any resources available for us there?
That is an excellent question. I do, not off the top of my head right now. Can I share them with you to pass on to everyone later?
Yes,
okay.
Absolutely.
Qualitative is honestly, in some ways, much more complicated. I'm a quantitative person because I like numbers, but also because to do qualitative well takes a lot of work. It is really work intensive. It's worth it, but it takes some work. So I will include some like a primer of steps for qualitative research, because I do think it's very worthwhile for people to explore and get into. I think we put a lot of emphasis on quantitative data when I think most of us know that it doesn't capture truly. There's a richness and experience that we can't capture with numbers. I can say, people like the session, but what did they like? Was there free lunch at the session? I mean, there's all sorts of things that we don't capture very well when we have just quantitative data, especially if we ask the wrong questions. And sometimes you don't know the right question to ask until you actually give people the opportunity to share those thoughts. So let me see. I will, you know what, let me save this as a PDF. Would that go through? Because I feel like it might not. Would a PDF be a better format, or would the PowerPoint be? I don't know how long. I know in the last session some people had difficulty downloading it.
Yeah. We also have another question there, Dr. Newell. Would you be willing to answer questions if students were to email you?
Absolutely. Absolutely.
We have another question in the chat. Do you recommend we still encourage students to do hand calculation? So we have a teacher who has their students do t-test calculation, Pearson's R, and an ANOVA by hand. Oh, wow, that's tough.
So my thought process is this. While it is useful to have an idea of what the underlying work is happening, it's useful to have an idea of how these things are working, that it's not a black box of I drop data in, I get magic out, to understand if things don't work, why they're not working and what's happening. On the other hand, I also will say that in this day and age, because of all the access to calculations, it might be useful, if you're going to do that, to give them, instead of just like the fundamental, like let them know what the fundamental underlying, especially when you get to ANOVA, the underlying things are, and then say, okay, we're gonna have you run it in the software first. And then when you get problems, troubleshoot. Why did that happen the way it happened? Because if they truly know the underlying things that are happening in that black box, then they're able to troubleshoot. And then that shows the relevance of it, because otherwise it just feels like busy work. Like, why are we doing this when I can do this, with software easily? It's super simple. I feel like that it shows the relevance a bit more when they have the opportunity to see where the shortcomings of the software are.
Great. Since you brought it up, where can we get resources for free software?
So my favorite free software, and I use this even though, I have access to SPSS and SAS and things like that. I use R, and it takes some coding, and there is a learning curve, but there are a ton of tutorials out there for it. And it's just and actually, let me pull up the website and I can drop that in the chat. It is free. It is open source, so if your students get really into it, they can create their own packages and codes for it. So it gets at some coding stuff if students are really, really interested in doing that. I use R, but I use R within R Studio, which is kind of like a wrapper for it, which makes things a little bit prettier and a little bit easier to keep track of. Like, it will turn my code different colors, so it's easier for me to see. Let me drop that in the chat. And it also has, no, R is not S. It's different. R Studio also has, you can use it with Python, and there's a way to communicate between the two. So if your students are already coding in Python or are familiar with Python, they can translate between the two coding languages. But it's pretty simple to get started. It takes some trial and error, and your students will become very, very skilled at Googling, how do I do this particular thing in R? And all kinds of amazing things come up. I still learn from it every single day when I'm trying to do something different. And it gives great visualizations. Visualizations in Python are probably prettier, but I am a big fan of R. Businesses use it, schools use it. I prefer it to other statistical software also, because it makes, even me at the stage where I am, it makes me justify my work. If I am doing a t-test on SPSS, you can go to a drop-down menu and just select all different things and never question why. You just pick them. With R, if I'm doing a t-test, and I'm like, okay, well, but what are my assumptions? Am I going non-parametric with this because I feel like my data is not distributed normally? How should I go about this in a different way? So, and then you can share your code with people. So students can send you their code, and you can say, okay, this is what you did. Why did you do this way? They can include notes, and they can explain why they included their code in a different way. I love R. I'm a big proponent of R. I feel like I probably never would have learned how to code anything at all if I hadn't started using R. So even students who are a little bit hesitant to get going with coding, and once you get going and start kind of figuring out what's going on, it makes it feel much more applicable to me, at least, in some tutorials I've seen where it's like, you're going to build a box. Well, okay, I'm using this code software to build a box, but why? I like purpose behind the things that I'm doing, and I think sometimes students do too.
Great. And I just want to throw out there, if you do need SPSS, I think SPSS still gives a free trial. So if your students need it, have them sign up for a free trial. But again, there is a learning curve in using SPSS too.
Yeah. Yes, very much so. I mean, it's with all of these, it's not an automatic like, oh, I'm going to plug my two numbers in and go from there. It's even with Excel, there's a bit of a learning curve sometimes for figuring out how the best ways to organize data, the ways to make it do things. So I will say with R, definitely be prepared for a lot of the learning curve for that. Like you probably want to do some work with it yourself before you throw your students into the deep end, because you start out with just kind of this blank slate and it's like, what next?
Well, any other, oh, there we go.
Yes, you absolutely can. In fact, there's a setting in Excel when you look at the different chart options where it'll give you the opportunity to do it. Usually what I do though is I basically draw my own. So I'll do like, if I know I want my error bars to be, or if I want like box plots, I will say, okay, I'm doing my box plots with, you know, we're going to do quintiles. I'm going to put those in, and I'm going to, you know, make sure that my mean, so you can put those values in, but it's also helpful to do that because you get to kind of spot check the values and go along. I'm big on doing a spot check on my data before I do anything. It's far too easy to throw a bunch of data into a figure and never question why things look the way they do.
Any other questions, guys?
I have a quick question.
Yeah.
So you suggested R, and if it is, and since it is a free software, I mean, I would definitely have my daughter look into it, but I think we need a book. I'm a book person, so can you suggest any book that is good to learn R?
Yes, I can. It is hold on just a second. I'm going to go, I'm going to grab it. Okay. This book, Discovering Statistics Using R, I like it because it's practical, it's easy to read, it's on Amazon. It is not cheap like most textbooks because apparently we can't have textbooks that are not, you know, heinously expensive. But it goes through everything, and it teaches you how to use R to do it without going overly into all of the, you know, some books that teach statistics get really heavy into the math, which can be really overwhelming for students and teachers alike. Sometimes it's like, I don't want to see all of the equations. I kind of want to know what this means, what I'm doing, and how to make it work. So it is by Andy Field. I like the way he writes about things. It goes from the very beginning, like how to set up data in R, all the way through really advanced statistics. If you wanted to do like a multi-level analysis because you've got a big data set of, you know, 50 classrooms with 30 students in each classroom, and you need to look at the, you know, you need to account for the variance among the different classrooms, you can do that using this book. So, I mean, I still use it even now. It is my statistics Bible. Or
thank you so much for the reference.
You're welcome. You're welcome.
All right. Well, guys, thank you for joining us during Dr. Newell's session here. She did put in quite a few of her information here, so feel free to email her with any follow-up questions that you all might have. Also available is her presentation there in the chat. So we're going to go take a 5-minute break in between our next session, which is going to be the roundtable discussion about how to host a science fair virtually. And our speaker there for that session will be Miss Lisa Woolley. So go ahead, stick around, go grab your lunch, and join us in a few minutes. Thank you, Dr. Newell.
Thank you, guys. It's been super fun.